Good morning, good afternoon, good evening. Welcome everyone to a session on atmospheric and subsurface radionuclide background and dispersion. My name is Jolanta Kuśmierczyk-Michulec. I'm the convener of today's session. With me is Jonathan Barret. He is our moderator. Today we will have 7 presentations. Each of the presentation will be for 15 minutes in total. It means the presentation itself and time for a few questions. We will follow the order that is also listed in the program. So our first presenter will be Pascal Hakim, then Giuseppe Ottaviano. The next presenter is Mohamed Mahmoud Munia, James Ely, Christian Lauer, James Harvey, and Tim Johnson. So let's start with the first presenter, Pascal Hakim. Screen is yours.
Good afternoon, everyone. Pascal and me will now present you the results of the 6 months of test of the SPALAX New Generation system at CA near Paris in 2019. So to begin, a short reminder of the key features of the SPALAX NG system. It is produced by CGLEC Defense in modular or in shelter version. The sampling duration is configurable also from 4 hours to 12 hours. It is based on the use of membranes on adsorbent, charcoal and silver exchange zeolite. And the detection system is high-resolution beta-gamma system that gives low interferences and high data quality. And that also gives high sensitivity for the 4 relevant radioxenon isotopes from 0.1 millibecquerel per cubic meter in 12 hours to 0.5 millibecquerel per cubic meter in 4 hours. And the system is now on the final acceptance stage of the PTS qualification program. So the qualification period, the first qualification period took place from October 18 to April 19 at the CEADIF facility near Paris. You've got here a picture. During this period, the data were sent directly to the IDC with a high data availability, close to 99%. The results validity of the station were confirmed by a certified lab intercomparison. Cross-contamination factor was far below the specification of 1%. And during this period, we obtained many detections, especially due to the high sensitivity of the system. You've got here the historic of detection for the 4 radioxenon on the period. In gray, the detection limit for the SPALAX NG, and the dashed line here is the detection limit for the SPALAX 1. As you can see, we improve a lot the sensitivity. And we've got also many detections thanks to the proximity, of course, of the Fleurus facility at about 300 kilometers from Paris. And more interesting, among this detection, we obtain many multi-isotopic detections that are interesting to study more in detail, and especially the. So regarding the isotopic ratio, the first one is a 131M on 133. As you can see, we got a high variability of about 2 orders of magnitude. It is especially due to the process and the separation of iodine. What is interesting is to see this point, these data, which are quite unusual ratio, and we understood that this ratios come from 2 different sources, a global critical background for the 133 and local iodine source for the 131M. You will see that at ATM study later, and it emphasizes a lot the importance of this kind of local source on the isotopic ratio. Regarding the 135 to 133 ratio, we got also a high variability of about 3 orders of magnitude, due especially to the short half-life of the 135 isotope. And a very interesting ratio is the 133M on 133. It is much more tight, and this ratio is meaningful, especially due to the direct filiation between both isotopes. So it is especially these thresholds that are used at the French NDC to discriminate from an event. And as you can see, we confirmed this threshold with only 2 data above this limit with a high uncertainty, so close to the critical level. These 2 data were considered as not significant. And the last point is the 4 isotopes Merck chart that are also possible to display thanks to the number of detections obtained. And we confirm also the usual threshold for these 4 isotopes Merck chart. So I give now the floor to...
Good afternoon, everybody. Thank you, Sylvain, for the presentation of the SPALAX New Generation features. I will present here an overview of the ATM analysis of the data collected by the system during the test period near Paris. As said before, the system has made many detections, including many multi-isotopic detections. This pie chart presents the occurrences of the number of isotopes in each sample. And for each case, a very simple analysis of the meteorological conditions has been performed. When no xenon has been detected, the winds were from southwest direction. When only one xenon has been detected, in most cases xenon 133 associated with very low concentrations, the corresponding wind rose is quite similar to the local general one, indicating that the xenon is due to the global industrial background. And the more isotopes are detected, the more the wind came from northeast direction with high wind speeds. This basic meteorological analysis allows to highlight a very dominant source located northeast of Paris. This is the well-known radioelement production facility in Belgium at Fleurus. Atmospheric transport simulations were performed to characterize the releases from the Belgium facility based on SPALAX measurements. The simulations were based on different wind fields in order to take into account as much as possible simulation errors due to the methodology. We have defined a small ensemble model that uses the meteorological data presented here and the Lagrangian dispersion model FlexPart. A first set of simulations was carried out using daily average source terms from the literature and for the 4 radioxenons. For xenon 133, we have added the calculated contribution of distant sources, NPPs, and medical isotope production facilities. And then we have reevaluated the required source term by comparing simulation and SPALAX measurements. The proposed source terms are given here in the right table. We note significant corrective factor for xenon 131M and xenon 135. The figure shows the comparison between simulations and measurements, and we see that a satisfactory agreement is obtained. This slide presents the comparison between measurements and our final simulation using proposed source terms. On the left, a multi-isotopic ratio chart is presented with 4 isotopes, and on the right, the same kind of chart, but with 3 isotopes. We have a quite good agreement between simulations and measurements, showing that the average source terms based on SPALAX detections are representative of real Fleurus releases. Obviously, the variability of measurements is not fully reproduced by the simulation, as we have considered average daily source terms in the simulations. To be comprehensive, we have also carried out simulation using real stack release data coming from the STAX monitoring program. The use of real release data allows to properly represent the variability observed in Paris. The comprehensive analysis of the detections showed that some low detections close to the MDC could not be linked to the releases from Fleurus or to the global industrial background. These samples involve xenon 135 and xenon 133, or xenon 131M alone or with xenon 133. For all these samples, ATM backward calculations and source localization have been carried out. And in all cases, air masses came from northwest, excluding Fleurus as the main contributor. We present here the case of detection of xenon 131M and xenon 133 on December 2018. Sylvain has mentioned this detection as the one with the highest xenon 131M xenon 133 ratio. During this detection, the calculated global background in xenon 133 was quite low, under 0.3 millibecquerel by cubic meter. The backtracking suggested that a local producer of medical radio elements using iodine 131 and located close to the Spallax in G at about 15 kilometers could be at the origin of the detection of xenon 131M. This is a quite complex situation because the isotopic ratio is calculated from two isotopes that may have different origins. It can be very tricky if such situation occurs after a nuclear test. So this is the last slide and our main conclusions on these 6 months of test of SPALAX New Generation in Paris. The data availability rate was higher than 99% with high quality data and with high resolution. The high sensibility of the SPALAX New Generation allowed a large amount of multi-isotopic detections. All these results led to reconsider our knowledge of the radioxenon background in Western Europe. And finally, we have pointed out that releases from local industrial sources may affect measured isotopic ratios. We should mention that the system was also installed in Canada, in Ottawa, for additional 6 months qualification period from December 19 to June 20, and that a similar study on radioxenon in Northern America is to be conducted based on SPALAX measurements. You can find all the results of this study in 2 papers recently published in the Journal of Environmental Radioactivity. Thank you very much for your attention.
Much. Thank you very much. So I'm not sure if Pascal and Sylvain are among participants. So anyway, thank you. It was a really very interesting presentation. Since we are close to the time for the next presentation, we will move to the second presentation by Giuseppe Ottaviano on statistical study of the IMS 133 xenon data distributions using both a parametric and a non-parametric method.
Distinguished colleagues, good afternoon. My name is Giuseppe Ottaviano. I am a physicist researcher at ENEA, Nuclear Security Division, Bologna Research Center, Italy. My lecture is about a statistical study of the radioxenon measurements at noble gas stations of the International Monitoring System of the CTBTO, using both a parametric and non-parametric method. The study was performed in collaboration with the Department of Statistical Sciences, University of Bologna, Italy. Let's take a look to the summary of my lecture. We will see an introduction, the methods, a case study, the results, and finally the conclusions. In order to monitor the atmospheric radioactivity, The international monitoring system of the CTBTO consists of currently operating 72 particulate stations, 14 laboratories, and 25 noble gas stations. The noble gas radioxenon is a fission product generated not only by nuclear explosions, but also by medical isotope production facilities, nuclear power plants, and nuclear research reactors. On the top left, the order of magnitude of radioxenon releases. On the bottom left, the positions of IMS stations, isotope production facilities, and nuclear power plants. On the right side, the overall radioxenon atmospheric distribution. Therefore, in order to distinguish radioxenon emissions by nuclear explosions from radioxenon emissions by civil sources, it is essential to study not only the radioxenon atmospheric background, but mainly its anomalous values that can be reasonably related to a nuclear test. The International Data Center of the CTBTO implemented since 2012 a radioxenon categorization scheme on top left that allows to identify anomalous values using the abnormal limit that is a threshold based on the median and on an interquartile filter. The abnormal limit is constantly updated at each radioxenon measurement, considering the last 365 observations. We will see a comparison between the IDC algorithm and the proposed method. Let's introduce the proposed method, the statistical process control conceived by the physicist Shewhart in 1924. The concept is that every physical phenomenon is subject to two types of variability. Natural variability sources, common factors, for which the phenomenon is in control, and systematic variability sources, specific factors, for which the phenomenon is out of control. The objective of the SPC method is to identify the presence of systematic variability effects of the phenomenon. Let's consider the parametric approach to the SPC method. This approach consists of two control charts, the single observation control chart, which is sensitive, and the EWMA control chart, which is sensitive to small variations. On the bottom left, the general structure of a control chart with a central line and an upper control limit and a lower control limit. On the right side, the equations of the lines for both the control charts. Let's move to the non-parametric approach to the SPC method. The recursive segmentation and permutation algorithm, suitable for both univariate and multivariate analysis, consists of two control charts which allow to identify changes in the mean value and in the variability of the phenomenon. The main feature of the RSP algorithm is the possibility to quantify a statistical significance through the calculation of a p-value. Both the parametric approach and the non-parametric approach were applied to the 133 xenon activity concentrations measured at the IMS MNX45 Mongolian station. Let's take a look to the result of the parametric approach. This is the overall chronology with 450 observations from 2013 to 2018, and the red line is the abnormal limit calculated at the most recent observation. From the end of 2014 until the middle of 2018, several anomalous values above the abnormal limit were recorded. The single observation control chart shows 43 red points, that means 43 anomalous values above the upper control limit, with a clear increasing trend of the anomalous values. This control chart also allowed to identify systematic trends of the phenomenon when, for a fixed period, more than 7 points are between the central line and the upper control limit. The EWMA control chart shows 304 red points, that means 304 anomalous values above the upper control limit, with again a clearly increasing trend of the anomalous values confirming the outcome of the single observation control chart. Let's move to the non-parametric approach to the SPC method. This is again the overall chronology of the MNX45 station with 450 observations in the same time interval. The recursive segmentation and permutation algorithm allows to highlight changes of the mean value, upper graph, and changes of the variability, lower graph. The algorithm was applied to 365 observations to be consistent with the abnormal limit and in order to allow a comparison. The plus value of the RSP algorithm is the quantification of a statistical significance through the calculation of a p-value. The confidence level is set at 95%, and in both cases, the calculated p-value is lower, and this means that there are statistically significant changes in the mean value and in the variability. This graph shows the comparison with the IDC algorithm. The RSP analysis identifies changes in the mean value and in the variability corresponding to the anomalous values identified by the abnormal limit. In other words, the RSP algorithm confirms the anomalous values above the abnormal limit. But the innovative main feature of the RSP algorithm is the statistical significance of the identified changes. In other words, the choice of a confidence level allows to produce for each anomalous value a statistical significance statement through the calculation of a p-value. This graph shows between the two control charts of the parametric approach to the SPC method and the IDC algorithm for the anomalous values recorded at the IMS MNX45 Mongolian station. The single observation control chart shows a slight difference with respect to the IDC algorithm, but the EWMA control chart shows a big non-parametric RSP statistical algorithm allows to identify significant changes in mean and or variability through two specific control charts. The calculation of statistic for the identification of mean and or variability can be also used to identify trends or oscillatory behaviors of the phenomenon, statistical fluctuations. The algorithm was applied to 365 measurements at the IMS MNX45 Mongolian station to be consistent with the IDC algorithm. There is a good agreement between the anomalous values identified by the IDC algorithm and the changes of the mean values and variability identified by the RSP algorithm, which furthermore allows to associate significance values to those anomalous measurements identified by the IDC algorithm. The RSP algorithm could be therefore a plus value to the IDC through the quantification of a significance level. When several single anomalous values are grouped above the abnormal limit, then the RSP algorithm is able to identify a statistical significant change of the mean value and the variability. It may happen that single values above the abnormal limit don't correspond to RSP changes, and this means that those single anomalous values above the abnormal limit can be mere statistical fluctuations. In other words, those RSP changes that correspond to grouped values above the abnormal limit should be further investigated, and the RSP algorithm could be useful to identify mere statistical fluctuation of the phenomenon. While the abnormal limit is able to identify all those values above a calculated activity concentration, the RSP algorithm is able to identify among them those changes that are statistically significant, providing a through the calculation of a p-value. Furthermore, the RSP algorithm could be useful to retrospectively understand what may have happened in the considered time intervals. In other words, the RSP control charts could be used to perform periodical retrospective monitoring of the data measured at the ISMS stations in order to understand the causes of significant increases of the mean value and or variability. Finally, the RSP algorithm could add a plus value to IDC method, and the joint use of the two methods could be useful to achieve an improvement for the general methodology. That's all. Thank you for your attention, and arrivederci.
Thank you very much. I think we have one of the co-authors of this presentation, Antonietta, among us, so maybe she can. Antonietta Reza, no? And Ottaviano is also not. Okay, so I would like to ask all participants and presenters that they would be with us, so the question that will appear in the chat can be answered by them. So I think many people are very interested in the presentations and in the opportunity of some kind of interactive exchange of information. So please stay with us and be available for online responses. We still have some time for the next presentation, and I was instructed not to start before because other people may want to listen this particular presentation. The next speaker will be Mohammed Mahmoud Mounia. He will talk about statistical study of the cesium-137 detections at station RN43. So I think we can start preparation for this presentation, but I know that Mohammed is among us. Yes, he is on the list of participants. So Mohammed, please stay till the end of the presentation, and if there will be any questions from the audience, please address them. So I think it's time maybe to share the screen. We will share the presentation for you.
I am Munja Mohammed Mahmoud from Mauritania. I am the responsible of National Data Center. And I am going to present a preliminary study on the detection of cesium-137 at station RN43 with the aims statistical approach and process control charts. This work is the result of a joint collaboration between the Italian and the Mauritanian National Data Center. The historical analysis of the accuracy of relevant radionuclide at RN43 over the past 10 years showed that the main contributor was cesium-137, causing several level 3 and level 4. A descriptive of the cesium-137 accuracy was performed and two types of parametric process control method were applied: the Shewhart control chart and the exponentially weighted moving average (EWMA) control chart. The result of both methods were then analyzed in order to reveal seasonality, possible sources of the cesium-137, and correlation with atmospheric phenomena. So you will find more detail about this method in the presentation by the Italian NDC meeting. 3 has been established in Mauritania in 2006, and it is located in a military zone near the capital Nouakchott, and it is under the responsibility of the National Nuclear Regulatory Body, RSN. The Mauritanian NDC has been established in 2019, and I am the responsible of its activity. So the establishment of our NDC was years after the establishment of our station. In order to study cesium-137, we have analyzed the data of atmospheric particulate on the capital city, Nouakchott, made by researchers, Emitter and Daimi, and published in that in-depth journal in 2008. The atmospheric optical depth is the coefficient of attenuation of solar radiation by atmosphere. So it is an indirect measurement of the presence of dust in the atmosphere. The graph reported the aerosol optical depth in the period between 2000 till 2013. From this data, possible to evaluate the aerosol loading for the same period. The atmospheric aerosol loading is the measurement of suspensions of solid and or liquid particular in the air that we breathe, as dust and smoke measured by the mass concentration of aerosol particles or by an optical measures. So we have here focalized in data in the period between 2008 to 2013 because we have analyzed the cesium-137 measurement in the same period. It can be noted a clear similarity of the aerosol presence in the air on the capital, showing a lower aerosol loading in the central month of the year. Here we applied the parametric method to the cesium-137 dataset by the Italian NDC. Consists of two types of control. The first one is chart, it's the Shewhart control chart, that is single observation chart, sensitive to large verification with respect to the mean value. The parametric method applied to the cesium-137 data by Italian NDC consists of two types of control chart: the Shewhart control chart and EWM chart, sensitive to small verification with respect to the main value. More detail about this method will be presented by the Italian NDC in oral presentation during this conference. The descriptive analysis of the distribution of cesium-137 measured at RN43 showed a strong of the distribution. So we have applied two box-Cox transformation to enhance the systemetry, and the result. This value has been used for the following control chart. We have applied the Shewhart control chart, and you can see clearly that chart point on the signal due to Fukushima accident and also some small signals in 2007 till and 2008 till 2010. So we have Fukushima and the small signals. The same situation is shown with the EWMA control chart, but other anomalies can be found. This event can be correlated with high aerosol loading. So, coming to the conclusion, we can summarize that we have studied some statistical approach to the measurement we registered in our IMS radionuclide station located in Nouakchott, and we have applied the process control charts to the data set, and it was clearly that the control charts could help the deviation from of the measurement. We have noticed some coincidence with the appearance of cesium-137 and augmented aerosol loading on Nouakchott in spring 2007 and 2008 till 2010. New dataset on atmospherical aerosol loading will be searched for further study to investigate correlation will be done in the future. Thank you to the collaboration between Mauritania National Data Center and the Italian National Data Center. Thank you.
Thank you very much. It was a very interesting presentation. We have the first author of this presentation, Mohamed Mahmoud Mounia, with us. I think we have some question for you. So the first question is, did you try to apply on some more recent events your method, the events which are less visible through the IMS network? Do you hear us? I think he's
we requested a mute. He needs to click to.
Okay.
I didn't tell you when. What's the question?
The question was because you applied your method to some major events like Fukushima and so on. So did you try also to use data from more recent events? To other events?
I heard a little, but there is the other question, the bigger part of the question I didn't. Sorry for that. Very bad connection.
Okay, so maybe I will try another question. Another question is,
if you can write the question. If you can write the question by chat, it will be.
I think this question is in chat. Can you check the chat for questions?
Didn't hear them.
Pick up the.
I will use the. So if you can question the chat, it will be better. The question clearly.
Good afternoon. Can you hear me?
Can you hear us?
Yes, now it's better.
Okay, so indeed there are two interesting questions, three now in the chat. The first one is from Ted Boyer, and the question is, does your cesium-137 distribution appears to be log normal? And I give you the floor to answer that question first.
Can you unmute yourself?
I didn't hear anything. The voice is so.
But do you have access to the chat? Because the questions are in the chat, so you can check them.
I cannot see the chat. Can you see the chat?
No. I can't see the chat.
Okay, the question
Okay.
in the chat. Yeah, in the chat.
My Italian colleague, she has a good connection. She will answer the question by writing. Do you hear me?
Yes, and so you prefer that Antonietta will respond to the questions? Okay, so maybe we can ask Antonietta. Antonietta, do you have better connection to respond to the question related to this and previous presentation? Antonietta Rizzo, yes, that's one.
Hello? Can you hear
Hello.
me?
Yes.
Can you hear me?
Yes, we can hear you.
But you know, Yolanta, I can. You can hear me, but I cannot hear you. I don't know why.
So you can hear me?
Okay, now I can hear you. Not through the headphone, but the device. That's right.
There was a question in the chat, so if you could read this question in the chat, then we can address maybe this one.
Please, can you read me, because I don't see it.
So the question is in the chat.
Perhaps Giuseppe is connected. Do you see the chat? Because I don't see any chat.
Good afternoon. Hi, Antonietta or Giuseppe. Can you hear me?
Yes, I can hear you.
Okay, very good. So I will read the questions, the 2 or 3 questions we have in the chat on the event platform, and maybe you can address them one by one. Does it sound fine with you?
Now I can
Maybe
read one question in the chat. That is, does your cesium 137 distribution appear to be log normal? This is a question.
Yes.
Okay, the question is no. As we analyze the data, the cesium 137 distribution in the period 2018 to 2018, it was strong asymmetrically distributed. So this is why apply control chart process. We need to correct this asymmetry, and we applied the Box-Cox transformation in order to have a more symmetrical distribution. And after we applied the control chart process distribution. This is quite an important thing to consider, because a lot of stations are considered to log normal distribution, but we realize that this is not the case. So also the statistic that we can apply on them should be a little bit better considered. Did you hear my answer?
yes, thank you.
Thank you.
Thank you.
Maybe I can read another question that we had in the chat, and it will be the last question for this presentation. Question from Martin Kalinowski. I'm reading. So this e-poster shows that the cesium-137 observation at RN43 is mainly occurring when the wind is coming from a narrow zone. Could you apply a correlation of the control charts with the wind direction to identify anomalous origin directions? Sounds like a very accurate and complicated question, actually.
Yes, this is a very, very, very good question, very nice. This is what we want to, because in the atmospheric aerosol loading and the occurrence of cesium-137 that we also saw in some neighboring station, IMS station. So this is just a preliminary observation. But for sure, now we want to try to have more information about direction and aerosol particles in order to make a better and more depth analysis of this phenomenon. So, I want just to say that this was just a first study collaboration that we ran with the Mauritanian National Data Center. So we would like them to be better involved in finding information about wind and composition of the aerosol, so that we can apply the control chart.
Okay, thank you very much, Antonietta. We will move now to the next presentation. So thank you, Antonietta. Thank you, Mohammed. We move now to the next presentation.
Thank you so much.
So the next presenter is James Ely. First observations of environmental xenon 125, 127, and 129 M.
Hi, I'm James Ely, and I'm going to be talking about some new observations of radioxenons. This work was done by my colleagues and myself at the Pacific Northwest National Lab. I wanted to highlight Justin McIntyre, who did a lot of the analysis before he retired. I'm going to talk a little bit about the observations. We saw these on a system called the Xenon International, and some of the anomalous data that we saw, and how we analyzed that and determined their new radioxenons, and then talk about a potential source for these radioxenons, the challenges and mitigation strategies, and a little bit on conclusions. We observed these on a system called the Xenon International, which is a next generation of automated radioxenon collection and measurement systems. And this system was developed at the Pacific Northwest National Lab and transferred to Teledyne Brown Engineering at their manufacturing facility in Knoxville, Tennessee. This system is a next generation compared to the current international monitoring systems, and collects xenon in about half the time, in 6 hours, and collects about twice as much xenon in that amount of time. So a very sensitive and capable system. Teledyne Brown has been testing this system over the last year. This is just some of the data that I will be showing that it came from this data set. And they were doing testing, so turning the system on and off, so the data has dropped out in some places. But what's important here is that when the system is operational, it is very stable and collects about 2.5 cc's of xenon in the 6-hour collection period. When we first started looking at the data, we didn't observe anything unusual. The 133 was detected quite often, but that's not unusual. And the same with the xenon 135, we often detect that as well. But then we started seeing the 133M detections, and that the 133M was at a higher level than the 133, which is unusual. And there are also a large number of 131M detections, although that's not shown on this slide. Digging in further, we noticed that the gamma ray spectra shows some unusual peaks. So this doesn't look at all like our normal radioxenons. And going in a little bit further, we started looking at the two-dimensional plots. And on the left here is our region of interest analysis type of a plot, where we have the energy of the beta on the x-axis and the energy of the gamma on the y-axis. And these boxes represent regions of interest that we pull out the different radioxenons from. So we count the signals in these regions of interest. The Xenon International System separates out xenon, so it's unlikely to be another nuclide. However, it could possibly have been radon, although there doesn't seem to be any signature in the ROI1, which is the radon ROI, which lies between 300 and 400 keV on the gamma scale. We do see this large signature in around the 500 keV, which is not consistent with the normal radioxenons. So we started looking through all the data and separating out what we found were different signatures. We were able to isolate 4 different signatures, 3 radioxenons and 1 iodine. And by looking at the publication on the nuclear decay data, we were able to identify xenon 125, xenon 129M, and xenon 127. This is the decay scheme for xenon 125, quite complicated, and a lot of gamma rays and ways that it can decay. Xenon 125 has a 16.9-hour half-life, so fairly short-lived, and it decays via positron emission. So the positron interacts with an electron and creates 2 511 keV gamma rays, which are picked up, and although not always picked up in the beta detector, occasionally it's picked up and with coincidence of the other 511 keV shows up in our beta gamma spectra. But it also shows up quite strongly in the gamma spectra, which is shown on the right here, where we have the gamma singles in the blue and the beta gated gamma in the red. And then there's also a lot of other gamma ray peaks. There's a lot of gamma ray emissions that are detected, and some of these gamma rays are converted and turn into conversion electrons or Auger electrons and X-rays, and we can pick those up in the beta detector, and causes a beta gamma coincidence, which is detected. Here's a plot of xenon 127. You can see that it's missing the 511 keV peak, so it's distinct from the 125. And here again, strong gamma ray detection, so strong gamma singles, but a lot of these are also converted, and so we have the beta gamma coincidence spectra as well, but a unique signature all of its own. And then we have the xenon 129M. This one was hard to isolate. In fact, this is a sample from, this is a measurement from a gas background sample after the sample measurement. And so this is where the sample has been removed, so there's vacuum in the beta cell, and but this is some memory left over, some xenon 129M that was left in the cell, and we see a nice signature of this. There again, distinct from the 125 and also the 127. We also identified samples again as gas background of iodine-125, which is a daughter of xenon-125. So only xenon goes into the cell, but some of that decays into iodine-125 during the measurement process and gets trapped in the cell, either plated out on the inside of the beta cell or actually absorbed into the plastic, and causes a signature in subsequent samples. This is actually mostly accounted for in the current analysis, which uses the gas background to quantify and subtract out any memory or cross-contamination from sample to sample. The most likely source of these xenons is the high-flux isotope reactor at the Oak Ridge National Laboratory, which is about 15.5 kilometers away. The ratios and the isotopes are consistent with air activation, and we believe that this is from the high-flux isotope reactor when targets are shuttled in and out of the reactor itself. The high-flux isotope reactor is a strong neutron source, having 10 to the 15th neutrons per centimeter squared per second, one of the strongest neutron sources in the world, and so activation of the air would not be unusual. We are doing some atmospheric transport modeling to verify the source, and preliminary results indicate that this indeed is the source. So these radioxenons cause elevated readings of our normal xenons, so elevated 133, 135, and metastable activity concentrations. So they are not what we want to report, and so how can we account for these? Well, there's possibilities, and it's theoretically possible to account for these either in a region of interest type of analysis, and this is just an example of how you might do that. So you look at the 511 keV region, for example, which is associated with the xenon 125, and then subtract out any contributions to the normal xenons from that quantification of that region of interest. The challenge here is twofold. First, we need to be able to calibrate this system so we know what the ratio is of xenon 125, for example, in all of the other regions of interest. And so you need a calibration source to be able to do that. And second, it introduces additional uncertainty. Every time you have an interference ratio and you subtract that out, you increase the uncertainty in your measurements. So if we don't need to include this type of analysis in the analysis, then that would be the best, but we may have to if these continue to be observed. So quick discussion and summary. We haven't observed these in the 20 years that the IMS has been collecting data, but it's possible that we were just unlucky and got close to the high-flux isotope reactor. But it's also possible that as we put more systems out and more sensitive systems out in the field, that we will see more of these observations. There are also new things like new medical isotope production facilities that are coming online and new types of reactors where we might see more of this type of air activation going on. It's theoretically possible to account for these. I showed you one approach with the region of interest analysis. There's other methods as well that we could subtract these out, but they're going to be a challenge to calibrate and to deal with the increased uncertainty. And so in summary, new xenons have been observed in the Xenon International testing and results in high or incorrect readings of our normal xenons. And memory effects will be mostly accounted for in our current analysis, so that's not a problem, but in the actual sample itself, if we see these isotopes, that will cause these incorrect readings. And we will need to update and modify the analysis if these become common in the future. So that's all I have, and I'd happy to answer any questions that you might have.
Thank you very much for this very interesting presentation. So we have the author of this presentation among us. He is ready to answer the question. So we have time for maybe one question, and one of the question is, do you have an evaluation of the source terms?
I'm not sure I quite understand the question, but we have looked at these and the ratios of these new radioxenons is consistent with air activation. So that's why we believe it is from air activation.
Thank you. So I will ask, there is one question in the chat. I don't know, do you have access to the chat or should I read it?
I do have access to the chat. Which question are you referring to?
It is this question, since those non-traditional radioxenon isotopes are produced by activation, not by fission, and you believe that high FIR is the likely source, did you check CTBT relevant radioxenon isotopic ratio appear like from an activation source?
No, at this time, we have not done the isotopic ratios analysis. That's a good thought, and we will put that on the list to look at that. Thank you for that question.
Thank you very much. And I think it's time to go to the next presentation. Thank you. So next presenter is Christian Maurer, and he will talk about the results of the third ATM-Challenge.
As most of you As most of you probably know, the third ATM-Challenge is an international effort which has two main aims. First, to investigate the added value of stack emission data, and second, to investigate the added value of training an optimum ensemble. Let us first answer the following question. What is the average benefit over all four investigated stations, CX-17, DEX-33, SEX-63, USX-75, and all samples for June to December 2014, and all submitted runs of using actual historic daily stack emission versus average literature emission data for IRE and CNL facilities, and including rough estimates for NPPs and other facilities emissions. We tried to answer this question based on different metrics. As you can see listed here, you find respective values in the table, which is presented here. So what are our answers? Unfortunately, there is no average benefit from daily stack data over all samples and independent of the score used. But there is an indication of a positive impact of roughly estimated emissions of NPPs and other facilities that adds up to 20%. Now let us have a detailed look at statistics per station, flagging main emitters' influence based on ATM. From left to right and top to bottom, you find results based on all samples, based on above MDC samples, based on 50% influence samples, and based on 80% influence samples. And when you look at the results based on all samples or above MDC samples, you will find a quite fuzzy picture. There is one station for which stack emissions outperform literature emissions based on all metrics. There are two stations where literature emissions outperform stack emissions based on rank, but not on the so-called Seibert skill score. And there is one station where literature emissions outperform stack emissions based on all metrics. And it is only when having a look at those samples where we have 50% influence or even 80% influence that we will get what we want. However, it should be noted that the difference between using literature emissions and actual stack emissions is very minor. A different perspective is selecting samples based on the deviation of the actual emission profile from its average. Here you see the CNL emission profile, and the station investigated is USX75. It is clear that the sample is related to more than just one daily stack emission. What do I find? In 2/3 of the cases, the CNL contribution alone does not explain the signal, so something is missing. Nuclear power plants and nuclear research reactors and other facilities contributions are always in up to 2 orders of magnitude smaller than CNL stack emission-based contributions. So CNL is the driving force. And over all samples investigated here, stack data are beneficial in 2/3 of the cases. And as you can see from the first sample of the list, it can be absolutely important to know the actual stack emission value. Here, the analogous analysis for IRE and station SEX63. Here we find that for all cases, the IRE, and in one case CNL contribution alone, does not explain the signal, so clearly something is missing. Nuclear power plants and nuclear research reactors and other facilities contributions are in 2/3 of the cases and up to 2 orders of magnitude bigger than IRE stack emission-based contributions. IRE is not the driving force for these samples. And this also becomes evident when looking at the table below. For all samples, if you calculate MIPS contribution based on stack data or MIPS contribution on literature data, it is not at all clear which kind of input data set performs better. It really depends on the remaining contributions. Nevertheless, as for the previous analysis, stack data are beneficial in 2/3 of the cases. At this point, it is important to remember the PTS pilot study regarding the monthly xenon background in 2014 of our 4 investigated stations. First of all, there's a clear difference between the 2 European stations and the 2 stations located in North America. This is due to the fact that CNL clearly had highest annual values amongst all operating stations at this time. But it is also evident that knowing exact IRE emissions is clearly not enough for DX33 and SEX63. For example, looking at the synoptic situation in November 2014, it is understandable why stack emission data will hardly significantly outperform literature emission data at station DX33. Now let us have a look at the ensemble and its redundancy. On the left side of the slide, you see the Dallagrand diagrams, also called rank histograms, for the 4 stations investigated. Dallagrand diagrams are constructed via ranking all ensemble members for each prediction from lowest to highest, and sorting in the related observation into a bin made up by 2 adjacent ensemble members. In addition, there are 2 bins for the extreme values, that means observations not covered by the ensemble. What do we find? Unfortunately, there's a high redundancy within the ensemble. The Dallagrand diagram is not evenly populated. Or to put it in other words, Any prediction that repeats another within the same bin is a lost opportunity to fill others where no simulations are as abundant and makes the ensemble ineffective. Especially the ensemble is highly overpredictive for very small concentrations. But this is likely due to setting below MDC concentrations to 0 and is thus not related to the models themselves. Another way of looking at the problem is calculating the number of effective members that are sufficient to cover the variability of the observations. Let us define metric D, which comprises the error of model M, EM, the Pearson correlation coefficient between multimodal average error, MME, and error EM of model M. Then calculate the eigenvalues, lambda, of the correlation matrix, which elements are made up by the metric D. And finally, we form the ratio of the square of summed eigenvalues over the sum of squared eigenvalues for the overall period. And we end up with the message that 2 to 4 members are sufficient to cover the variability of the observations, but not necessarily the very same 2 to 4 members at every station are involved. In the next step, let's try to optimize the ensemble results via finding the ensemble combination which maximizes the rank. As for the calculation of the number of effective ensemble members, we find that just a few members is good enough for this purpose. However, we are dealing right here with a different time frame, just covering 3 months, split in a training period and an evaluation period. The optimum ensemble outperforms the full ensemble for all stations according to all metrics within the training period. And beyond that, with some disagreement in the Seibert skill score, the best ensemble or the optimized ensemble even outperforms the best model. Within the evaluation period, we see that there is a slight added value of using the best optimized ensemble compared to the full ensemble. And the added value is even considerable when looking at station DX33. However, it should be noted that our analysis is based on a very specific rank metric, indicated in all 4 blocks via filled circles. If we would use another metric, indicated here via filled squares, results will look a bit different. Now let me come to my conclusions. A huge data pool of modeling results has been created. Please request it from ZAMG or CTBTO. A more thorough statistical analysis, maybe a PhD, would be desirable. I really would like to emphasize this. It seems to be important to select samples appropriately to demonstrate an, on average, small added value of stack emissions from IRE and CNL alone. However, there is considerable benefit from this stack data for individual samples. It is interesting to note that the mere selection of samples partly or predominantly influenced by IRE and or CNL pushes the scores up most. The relative increase in scores on average adds up to 15% when switching from all above MDC samples to those with 50% or 80% IRE, CNL influence using literature emissions, compared to 7% when additionally switching from literature to stack emissions for 50% or 80% influence samples. This demonstrates on one side that knowing a large emitter and its location, as well on the other side, a proper average emission is more important than knowing the exact emission profile. And implicitly suppressing samples with overprediction in the sample selection process, as done via an absolute difference metric, can further enhance the scores, which demonstrates the effects of the transport error on scores. Simulating the radioxenon background at CX17 without selecting samples according to CNL influence seems to be especially promising, since CX17 is a remote station with, at the time of 2014, dominating CNL influence. It seems to be very important to gain more knowledge about non-IRE and CNL-related emissions for 2014. These emissions may be small individually, but in any case there are some, depending on the predominant synoptic situation, is a decisive factor in accurately predicting the radioxenon background at IMS stations. The existent full ensemble is highly redundant. If individual members cannot be made more diverse, a few submissions are good enough to forecast the xenon 133 background. This characteristic is related, example given, to dominating transport models, dominating methodological input, or to the fact that methodological input consists of analysis concatenated with short-term forecasts, thus reducing forecast uncertainty. The effective ensemble size is, as demonstrated, below 5. However, depending on the station investigated, the time period considered, and the individual members involved. A preliminary study shows that the reduced optimized ensemble at each station has slightly higher scale compared to the full ensemble, also for an independent evaluation period. And with this, I would like to thank you for your attention.
Thank you very much for this interesting presentation. Unfortunately, we don't have time for the next question, but maybe if we will have still time at the end, so Christian, please stay to the end of the presentation, and we will move to the next presenter. The next presenter is James Hardy.
Thank you for being available today for me to discuss with you about NorthStar's Moly-99 production program without the use of uranium and consequently without the generation of xenon. NorthStar began neutron capture production of Moly-99 in November of 2018, following the approval of our new drug application by the U.S. Food and Drug Administration. We utilized the Missouri University Research Reactor, and we have successfully shipped Moly-99 for more than 2.5 years with greater than 99% reliability. Our electron accelerator production program is expected to start U.S. production in January of 2023, pending FDA approval, and that will be located in our Beloit, Wisconsin production site. Both production methodologies will be used to supply the U.S. market and potentially the rest of the world. This provides a dual production approach that ensures reliable production and delivery of Moly-99. Both of these approaches use NorthStar's FDA-approved Radiogenics technetium-99 generating system. It uses our non-uranium-based produced Moly-99 to generate technetium-99M for patient use. The neutron capture method has identified no additional xenon production. NorthStar, or MUR, the Missouri University Research Reactor, does perform stack monitoring for xenon, krypton, and iodine release as part of their overall operations. The reactor operators do not believe NorthStar's Moly-99 production changes any of their monitoring goals because it is a non-uranium-based production methodology. Why do we use non-uranium-based? We do it because we can use stable molybdenum target material, molybdenum-98 isotope for neutron capture, and the molybdenum-100 isotope for our electron accelerator production. In both cases, the target material, the starting material, has uranium and thorium in the starting material at less than 20 parts per billion. Now let's talk about the electron accelerator production process. We've looked at potential xenon production from this process. It's a very clean process. Starts with accelerating an electron. The electron impinges upon the Moly-100 target assembly. The electrons are converted to Bremsstrahlung or X-ray in the target. The high-energy Bremsstrahlung then excites the molybdenum-100 target nucleus, ejecting a neutron and, of course, leaving residual Moly-99 that we can extract. We use enriched Moly-100. In nature, molybdenum-100 isotope is about 10% abundant, and we use enrichments or concentrations of greater than 95%. This particular production process has been known for more than 40 years, but never been applied on a commercial scale. Now, as far as an electron accelerator produced Moly-99, We have a target assembly that's capable of producing about 2,500 curies of Moly-99 per irradiation. That yields about 6 microcuries of total xenon inventory. This is spread among 11 xenon isotopes, and it gives us a total production of approximately 2 times 10 to the 5th becquerels per day of total xenon. As you will remember, the producer pledge was to limit xenon-133 production below 5 times 10 to the 9th. Well, our total xenon production spread among 11 isotopes is greater than 4 orders of magnitude below this maximum number. We've already noted that our neutron capture work at MER has no added impact. Thus, NorthStar could easily sign the radioxenon emissions pledge in June of 2014. Let's talk about where we are today with especially our electron accelerator program, since our neutron capture program is already in production. We have a 33-acre campus in Beloit, Wisconsin. You will see a large building that has a section on the right side with the outset on it that has our office space, non-rad production, administrative functions, customer service, etc. housed in that section. In the inset section to the left of the larger piece of this building is our processing building, our rad production building. This houses our hot cells, our fill lines, and all the support equipment necessary to process high-level radioactive target material. Further to the left, you'll see the first one of several of our accelerator production buildings on the site. This building houses our electron accelerators that have been delivered to the site. How is the inside of the accelerator building laid out? We have 2 IBA TT300 HE rotatrons. These are first-of-a-kind rotatrons that IBA has built. You see a picture of one there. These are rotatrons that are capable of beam energies of 40 million electron volts nominally and an average power of 125 kilowatts each machine. This allows NorthStar to have a very high production rate. They're individually housed in separate vaults, making maintenance much easier. You can see that each emits a beam that goes through a beam line and comes through the shielded wall into a target area. This target area contains a local target shield, and it contains the actual target assembly itself that is irradiated from both sides. Irradiating from both sides allows us to double production for a given target mass. There is also, you can see, a hot cell that is used to insert and remove the target assembly from the target station itself. You can also see in blue that there are dual helium production cooling system that is used on this process. The blue is the blower system. We have 2 of them in order to improve reliability of the system. And we, as I said, these move helium gas at high stream across the target assembly to cool it. This is a very robust setup, and it will be duplicated for our other processes and our other isotopes that we're going to talk about here in a moment. Let's take some other pictures and look at them. At the top, you'll see the building for the accelerator that houses the accelerators. It has also an office area on the front. This building is largely complete. We're addressing final punch list items at this time and commissioning the utilities today. On the right, you see 2 pictures of the TT300 HE accelerators on the day they were delivered in April from Belgium by IBA. In the middle picture, you see a picture of the inside of the accelerator building. You can see a nice epoxy floor, clean finish, a very open, easy access facility, easy to get around in, easy to process our our production processes within this facility. The vaults themselves are completed now that the accelerators have been installed. Also, you can see there's a roll-up door in that picture that we moved the accelerators through. The roll-up door has been removed, and now the last wall panels have been inserted in order to tighten in the facility itself. The beam lines arrive in July and will be installed in July and August. The local target shield and target station arrives in August and will be start to be installed at that point. And the target manipulation hot cell arrives in September and will be installed. We will have a fully integrated system ready to start operational commissioning in early fourth quarter this year. You can also see in the lower picture there a better picture of the helium cooling system. You can see the front cabinet there where one of the two blowers is mounted. There's a second cabinet you can see in the rear that has the redundant blower system. This is now undergoing commissioning on the site at North Star and will be connected to the target station when the target station is delivered in August. A quick summary of the program. Our neutron capture program again began delivering domestic Moly 99 to market in November of 2018. We've been doing this now for more than 2.5 years with 99% reliability. Our electron accelerator production is expected to start in January of 2023, pending FDA approval. Both locations and methodologies are used to supply not only the US market, but can also supply the rest of the world with molybdenum 99. Providing a dual production approach ensures the reliable production and delivery of Moly 99. These two approaches utilize North Star's FDA approved radiogenic system for generating technetium 99 from the molybdenum 99 we've produced. And this technetium, of course, is used for patients' injections. But I also want to point out that North Star will be making other therapeutic radioisotopes on our Beloit site with our electron accelerators. We have programs spinning up as we speak for copper-67 and actinium-225 production. And I want to stress that these are non-uranium based production processes that use our electron accelerators. North Star's Beloit site is a medical radioisotope production site that will produce large commercial volumes of multiple radioisotopes in the future without the use of uranium, and therefore will have no impact on overall xenon inventory. With that, I'd like to thank you for the time we've had today together and look forward to answering any questions.
Thank you very much. Do we have? No, we don't have. So if we don't have James Harvey among participants, then I propose to come back to Christian Maurer because there is a question in the chat and he may answer this question, and then we move to the next presentation. Christian, can you?
Yeah, you hear me?
Yes, yes.
Yeah, so what's the question for me?
Question for you is, can the ensemble membership be tested without doing the entire transport simulation? In other words, is ensemble investigation computationally expensive? So that was a question.
Yeah, so I think it is at least the way I have so far done it, because yeah, for determining the maximum rank, you need to try out all possible combinations for all ensemble subsizes. So this clearly puts some limits on the procedure. On the other side, yeah, with the methodologies applied by GRC and Stefano Galmarini, I think there there is a reduction of computational efforts possible. So this eigenvalue calculation and ratio formation, this is clearly not that computationally intensive. Whereas, as I said, the method I chose, and also Stefano Galmarini, if you would check the auxiliary material, so also the method Stefano Galmarini tried out using different metrics for optimization, of course, also require extensive computational resources.
Okay, thank you very much, Christian.
I would like, to still say something because Martin Kalinowski asked me to announce the next ATM-Challenge. So I think this is important. So for everybody interested, there will be a new ATM-Challenge to be launched in autumn this year. It will be different in terms of simulation length. So simulation length will be roughly 6 or 8 weeks, and we will look from a different perspective on the problem. This means the runs or the background, the simulated background, will not be simply evaluated using common metrics, which are widely used in atmospheric transport modeling. No, rather our aim is to try to find out whether, based on this simulated background series, we can screen out hypothetical nuclear explosions from a test data set. So we will have a test data set containing hypothetical nuclear explosions added to the actual background. This will be compared to the simulated background time series, and based on the ability of participants' background time series to enable such a discrimination, this background time series will be ranked or will be evaluated. Thank you.
Okay, thank you very much. So now we move to the next speaker. Our last presentation will be given by Tim Johnson. Tim, screen is yours.
Hello, my name is Tim Johnson, and I'm a geophysicist from the Pacific Northwest National Laboratory located in Washington State of the USA. Today, I'll be talking about an emerging method of imaging rock damage and flow pathways generated from underground explosions. First, I'd like to recognize my colleagues listed here from the Pacific Northwest National Laboratory and Sandia National Laboratories, and to acknowledge and thank the U.S. Department of Energy National Nuclear Security Administration for funding this effort. Today I'll be discussing a difference imaging method called time-lapse electrical resistivity tomography, or ERT, that enables us to image changes in the electrical conductivity of the rock caused by explosive damage or by alterations such as water evaporation during gas flow through damage zones. The work we have done to date shows that, at the scale of our experiments at least, geologic heterogeneity can have a dominating influence on damage patterns, even more so than the position of the shot. This is important because rock damage influences both the seismic and gas breakthrough signals that we use to monitor for underground nuclear explosions. In order to better understand those diagnostic signals and what they are telling us, we need to have a better understanding of rock damage. I hope to demonstrate that ERT can significantly improve our ability to do that. The general objective of our experiments was to investigate how explosive source characteristics, such as gas generation, influence detection signatures such as gas surface breakthrough times and seismic waveforms. Our test bed is in a massive rhyolite formation called the Blue Canyon Dome, located about 10 kilometers west of Socorro, New Mexico, in the USA. The upper right is a plan view of the wellbore layout, including the ground zero borehole and 2 rings of monitoring boreholes located 4.7 meters and 7.8 meters from the ground zero well. We use many different monitoring modalities, including seismic, gas, and ERT monitoring in each borehole, but focus here on the ERT monitoring. We conducted 2 shots, one 5-gram TNT equivalent at 60 meters below ground surface and one at 55 meters below ground surface, with the second having a higher gas production than the first. I'm showing on the upper left an example of the hardware we use to do the imaging. It's very simple and robust, consisting of stainless steel mesh electrodes strapped to the outside of a PVC casing in each monitoring well. Each electrode connects to a wire that leads to surface instrumentation. Here are plan and cross-section views of the boreholes. On the plan view, the red dots denote the top of the well and the black lines show the wellbore deviation. On the cross-section view, the red dots show where electrodes are positioned in each wellbore and the location of experimental shots 1 and 2 here. The blue dots show the location of gas sampling ports, which we don't discuss in this presentation. For a given ERT measurement, current is injected between 2 electrodes and the corresponding potential is measured between 2 different electrodes. Many thousands of such measurements are taken and analyzed using a tomographic imaging algorithm to estimate the bulk electrical conductivity of the host rock. Here is the baseline ERT image for the Blue Canyon Dome site before shot 1. It's important to note that the water table is well below our test site, so the site is unsaturated under natural conditions. In time-lapse ERT imaging mode, we monitor for changes in electrical conductivity over time by subtracting the baseline image from the time-lapse image, revealing only what has changed over time. In this case, that change is caused by rock damage. Our strategy was to first image the baseline unsaturated pre-shot bulk conductivity, which was shown in the previous image. We next inject water into the ground zero well to saturate the formation. Then we collect time-lapse ERT data and subtract the baseline image from the time-lapse images. The resulting change in electrical conductivity shows where the water went and therefore illuminates the natural fracture zones. In the next step, we execute the first shot, refill the ground zero well with water, and subtract the image generated in part 2. The resulting change in bulk conductivity shows where there is additional water compared to the pre-shot saturated condition and therefore shows the shot 1 fracture damage zone. In the next step, step 4, we do the same thing by executing the second shot, refilling the ground zero well with water, and subtract the image generated in part 3. And the resulting change in bulk conductivity shows the damage zone caused exclusively by shot 2. We then subtract the image generated in part 2 to reveal the total damage caused by both shots 1 and shot 2. In the final step, step 5, we injected heated air instead of water to induce a change in bulk conductivity within the fracture zone. When the warm air moves through the fracture zone, it evaporates water, decreasing the pathways available for electrical current flow and therefore decreasing the electrical conductivity. This region of decreased bulk conductivity revealed during the gas injection phase it shows where gas is flowing within the rock. This type of test can be used to illuminate damage zones and gas flow paths when it's not practical or possible to inject water. Note that for each shot, the package is lowered down into position and the ground zero well is filled with water and sealed at the surface to prevent water hammer effects from damaging the wellhead and compromising the containment. Let's now look at the results of each imaging campaign. In this slide, I'm showing the results of the first 2 steps, including the baseline unsaturated background ERT image shown in the blue to reddish color scale, and the change in conductivity that occurred when we filled the ground zero borehole with water, shown as conductivity isosurfaces in the purple color scale. The increase in conductivity at the purple isosurfaces shows where the injected water is going, indicating that there is an existing natural fracture zone where the water is migrating. We also conducted cross-hole seismic velocity imaging, which revealed a slow zone at the same location and provided corroborating evidence of a natural fracture zone. As we'll see, this natural fracture zone has a dominating influence on the damage patterns from both shot 1 and shot 2. This image shows the damage zone from shot 1, which was a 5 kilogram equivalent of nitromethane placed at 60 feet below ground surface in the shot hole. The imaging results are shown as isosurfaces of change in bulk electrical conductivity, where warm colors indicate an increase in conductivity caused by current flow through new water-filled fractures generated by shot 1. We see some damage formed around the shot location, but most of the damage occurs within the pre-existing fracture zone up here. This likely occurs because the pressure buildup in the ground zero well is released through the existing fracture zone, which pressurizes and extends or expands the natural fracture system. This result is much different than the conventional assumption that fracture damage should be primarily focused around the shot location. Shot 2 consisted of 5 kilograms of TNT equivalent of aminol, which produces more gas than nitromethane. The shot was placed at 55 meters below ground surface, or 5 meters above the shot 1 depth. This image shows the increase in conductivity is exclusively by shot 2. The result is like shot 1 in that the explosive energy is focused on the pre-existing fracture zones. Here we see increases in damage both within the natural fracture zone and the fractures caused by shot 1 at the 60-meter depth, but little damage around the shot 2 location here. There also appears to be less damage overall caused by shot 2 compared to shot 1, as the increases in bulk conductivity are muted for shot 2 in comparison to shot 1. And I'll show that comparison in the next slide. Here's a comparison of the damage caused exclusively by shot 1, shown here, exclusively by shot 2, shown here, and the total damage caused by both shots, shown in this fly around view here. And I'll just let that rotate for a moment so you can see the entire damage zone from both shots. The next 3 slides show time-lapse images of changes in electrical conductivity during and after the warm gas injection. This image loops through time-lapse change in conductivity during the injection phase. The changes are shown in isosurfaces, where green and cool colors indicate decrease in conductivity, and yellow and warm colors indicate an increase in conductivity with respect to baseline. During the 7.5-day injection period, we see decreases in electrical conductivity within a primary gas flow zone. This occurs because water is evaporating and removing current flow paths. We also see increases in conductivity above and below the primary flow zone around the injection well. This occurs because the rock is warming and behaves like a semiconductor, in that the electrical conductivity increases with temperature. And there is apparently less gas flow in these zones, and therefore less evaporation than in the primary flow zone here. Note that this primary gas flow zone occurs right at the upper margin of the damage zone that I showed in the previous slide. So here we're showing the time-lapse imaging results post-injection from 7.5 to 11.5 days as the system recovers to a new steady state. We see that the increases in conductivity fade as the rock cools. The decreases in conductivity also fade, but largely remain at the steady state condition. This suggests a permanent decrease in water content within the primary gas flow zone caused by the warm air injection and subsequent evaporation. Here's a fly-around view of the primary gas flow zone at steady state. Again, here the decrease in conductivity is caused by the decrease in water content within the primary gas flow zone. To investigate the feasibility and performance of ERT damage imaging without using a contrasting agent such as water or gas, we're also conducting laboratory experiments such as the one shown here. Here we have a core from a volcanic tuff approximately 20 centimeters tall and 4 centimeters in diameter that we instrumented with ERT electrodes as shown here in the black dots. We inserted an exploding bridge wire through the center of the core and detonated the wire, which produced a fracture approximately orthogonal to the axis and about 5 millimeters wide as shown in this X-ray tomography image. We then imaged the core with ERT electrodes. The fracture was evident as a decrease in electrical conductivity of approximately 1 order of magnitude. This occurs because the fracture electrically disconnects the rock across the fracture face, thereby decreasing the available current flow paths. Overall, this result bodes well for ERT imaging of rock damage without using a post-shot contrast agent. and efforts are underway to validate this through in silico modeling. We conclude with the assertion that improved understanding of gas and seismic detection signals requires improved understanding of rock damage from underground explosions. To date, our understanding of explosively generated rock damage comes primarily from numerical simulations, partly because rock damage has been difficult to observe. Likewise, rock damage data verifying and refining numeric simulations has been difficult to obtain. We have demonstrated here a new method of assessing rock damage patterns using time-lapse ERT imaging. Results at the Blue Canyon Dome site show that geologic heterogeneity dominates damage patterns for those experiments at BCD at least, and suggests that the effects of heterogeneity ought to be evaluated for other underground explosive experiments. Laboratory experiments have shown that rock damage can be imaged using ERT without post-shot contrasting agent injections. These results point to emerging ERT capabilities as a powerful new tool for understanding rock damage, flow paths through fractured rocks, and for improving damage simulations and understanding the gas and seismic signals we use to monitor for and diagnose underground explosions. Thank you for your attention.
Thank you very much for this interesting presentation. We'll check the question in the chat, but yes, Tim, are you with us?
Yes, I'm here. There was a bit of a delay with what was showing online, so yeah, I'm here.
Okay, so there is one question. So maybe we still have a minute to answer. Could you image underground damage features using a flat array on the surface?
Yes, in theory you can, but resolution decreases with distance from electrodes. So if it's a very deep damage zone that you're targeting.
Hello?
Yes, I'm here. I'm sorry. I was also listening to the online version, and it's there's a delay there. I was just saying that yes, you can image from the surface, and we do that often. But you know, if the damage is deep or the target is deep, you may not have adequate resolution to see what you want to see. So we often use borehole electrodes to improve the resolution we did.
Okay, thank you very much. So I think we just can conclude this session. Thank you very much to all presenters and my colleagues who contributed to having this session. Thank you very much, and see you on the next session. Bye.